Hello everyone, so this is the talk that I'll be giving at Codestock 2014, and this talk will be on programming the Nintendo Entertainment System. So the Nintendo Entertainment System, or NES, was released in 1985, and it was actually the first video game console that I owned as a kid, so programming a game for this system was something that I've always wanted to do. So when last month came around, they had a game competition, the Let 'em Dare Mini LD. The theme was to develop a game for a retro console. So I thought that would give me the perfect opportunity to develop a game for the NES. So first of all, I'll go over the architecture of the NES. The NES console itself is built upon a 6502 CPU. This CPU was used in many other systems such as the Apple II and Commodore 64. And in the CPU there is a 64 kilobit address space. You have an address range from 0 to 65,635, or in hexadecimal that would be from 000 to FFFF. And on the 6502, all addresses are preceded by a $sign. And on this system you have a 16 address bus, so every address will be represented by a 4-digit hexadecimal string. And also on the NES you have 4 registers. These registers are used for holding values. The first register is the accumulator. You can use that to perform mathematical operations or comparisons, things like that, on the value stored in it. Then there is a X increment register and a Y increment register, and basically those are used for storing values such as counters. And also there's a status register, and you can't actually write to the status register, but you can read from it to get certain values, like if the accumulator overflows, and it will put a status there saying that your value has overflowed. Secondly, the NES has an audio processing unit. Basically that is what plays all the sounds for your games and music and things like that. Then there's a PPU, which is the picture processing unit, and that you can think of that as like a graphics card, but it doesn't do 3D graphics or lines or anything like that. It basically does sprites, and that's all it knows how to do, is sprites and tiles. And finally, there's a lockout chip. Actually, on the game cartridge, there's a lockout chip on it as well. And whenever you start your NES, there's a key that gets sent between these two chips, and they perform some mathematical formula, and that determines whether the game cartridge is a valid cartridge. This was added as a measure to prevent unlicensed games from being played on the NES. Then on the game cartridge, you have a few components. First, the CHR, that's where all your sprite data is stored. Then you have PRG ROM, and that's basically read-only memory where all your game code is stored. And then some games had this WRAM optional memory, and basically that is used typically for things like save states and saved games, and sometimes these were connected to a battery, which allowed that memory to persist while the NES was turned off. So here's a simple diagram of the architecture of the NES. So at the top there you see the controller, and basically that's used for user input. That input gets sent to the CPU. Whenever you turn the NES on, the PRG ROM gets copied to the CPU, and also the CHR ROM or RAM gets copied to the PPU. And along with the CPU you see the APU there, which is used for playing the music and sounds. And then the CPU writes data to the PPU to modify the background and the sprites that are ultimately displayed on the television screen. And here's the address space for the CPU and PPU. So on the CPU, you can see the address ranges from 000 to FFFF, the 64K. The bottom 2 kilobyte is internal RAM, which can be used for things like variables and things like that. At address space 2000, you have your PPU ports, which you use for writing to the PPU. On top of that, you have the audio processing unit and controller ports for writing to those. And then you have the cartridge WRAM, things like the save games. And then finally, you have the game code itself, the cartridge ROM. Then at the very end of it, you have this NMI, reset, and IRQ vectors. So these are things that will interrupt your game code. So the NMI, which stands for non-maskable interrupt, for every frame that gets displayed to the screen, that's going to get called. And then from there, it's going to run all of the code that modifies your sprites and backgrounds and updates the game engine. And the reset vector, that gets called whenever the NES starts up, when it boots up, and also whenever the reset button is pressed. And finally, the RRQ, I haven't used that. It's used for special circumstances. Then over here on the PPU, you have 16 kilobyte of address space. And from 0 to 2000, you have the pattern tables, and that's basically all the sprite data. And above that, you have these name tables, and that's basically the arrangement of all the sprites on the screen that creates the background for your game. And on top of each of those, you have attribute tables, and that determines the colors that are used to paint the background. So you have multiple name tables and attribute tables, so you can switch between these to give different backgrounds in your game. And above all that, you have the background palette and sprite palette. You have a limited number of colors that you can choose from, and that's stored in these palette variables. So, in order to write a game for the NES, you have to use 6502 assembly, and I'll give a brief overview of how to write this assembly code. There's 3 major things that you use to write your game. So first of all, we have directives. And directives are used for sending special commands to the assembler. And all directives start with a period. Next, you have labels, and I think of labels kind of like a go-to statement in BASIC, how in the old BASIC code you would have a line number, and you could say go to that line number, then it would transfer execution of your program to that line number. So a label works the same way. Instead of a number, it's just a string, and you can jump directly to that string using a jump command. And all labels are not indented, and they are followed by a colon. And finally, you have opcodes, and opcodes are the bulk of your program. These are your program instructions, and all opcodes must be indented. So here's an example of some of the 6502 opcodes. You have your loads and stores, and basically these will load either a value or a value from an address into one of the 3 registers. These are the accumulator or the X or Y registers. And also you can take a value from one of those 3 registers and write it back out to the address space. You have a limited number of math operations. You have add, subtract, and I'll also mention that each of the values in your game are only 8-bit integers. So if you go over 256, it's going to overflow. So you got to take special considerations if your values are going to add to more than 256. You can also increment and decrement, basically adding 1 or subtracting 1 from the value that's currently stored in the register. And also you have a shift, which shifts the bits in your value, and that's essentially multiplying or dividing by 2. So you don't have a multiply, but you can have a multiply by 2. But you don't have any of the advanced math functions such as modulo or power or things like that. You got to write those on your own. There's a few comparison operations. These work like equals in a traditional programming language. Comp, if the value in the accumulator equals another value. You can also do the same thing for comparing to your X register or your Y register. Then finally, you have your controls, opcodes, and I mentioned previously the labels. Jump will jump to a label in your program. Then you also have BEQ, which means branch on equivalence. So if you do a compare operation and that value is equal to the value that you compared it to, then this will jump to another position of the supplied label that you gave to the BEQ command. And then you have B and E, which means branch not equivalent, which does the same thing only if the two values are not equivalent. So I created this as a way, if you're coming from a high-level programming language, how to sort of understand how assembly works. So first of all, we have declaring a variable. So in a traditional programming language, you just say int num, followed by a colon. And so in assembly, what you got to do is you got to use this directive rsset, and that tells the assembler where to start your variable in the memory address. And then after that, you specify the name of your variable followed by another directive .rs, which means reserve space, and then a value 1, which means reserve 1 byte of space. In a traditional programming language, to assign a value, you do that num, then an equal sign, then 42. To do the same thing in assembly, you're going to do a load into your accumulator, then you're going to specify that value. So all values in this 6502 are in hexadecimal. So 42 would be 2A, because 2 would be 16 times 2, which is 32, and A is 10, so you would add 10 to your 32, which gives you 42. And all like static numbers, which are preceded by a pound sign in addition to the dollar sign. Then you basically take that value in your accumulator and store that into your variable. To do an if statement, you see there on the left, you do an if, number equals 5 in a traditional language, then you do something. In assembly, you're going to load your variable into the accumulator. You're going to compare it to that value. So in this case, we're comparing it to 5. And then if it's not equal to 5, we're going to branch. If it's not equivalent, we're going to branch down to done, which means we're going to skip everything in the do something section. So you see there all comments in the 6502 assembly are preceded by a semicolon, where in a traditional programming language you might see something like 2 forward slashes. So a procedure in a traditional language, we would do something like void my method with the parentheses and open and close curly braces. Then we call that method just by using the method name, then 2 parentheses and a semicolon. Well, in assembly, in the 6502 assembly, we're going to have a label, my method, followed by a colon. Then we're going to do whatever we're going to do in that method. Then we're going to end it with an RTS, which means return from subroutine. Then later down in the program, we're going to do a JSR, which stands for jump subroutine. And then we're going to jump into that method. So once we jump to that method, then it hits RTS. It's going to resume control back at the next statement after the JSR. So to increment a value, so we got X, just assign 10, then you do a plus plus to add 1, or minus minus to subtract 1. In assembly, we're going to load that 10 to our accumulator, because A equals 10. Then we're going to store that value into our X register. Then we're going to increment that. You just call INX, and that adds 1 to it. And the same thing for decrementing. We store that value into Y, and then we're going to do DEY, which stands for decrement Y. To do a loop, such as a while loop, first we're going to, in a traditional language, we would set our counter to 0, then while our counter is less than a certain value, we're going to do something, then we're going to increment for every time in the loop until it does not equal or is not less than 255. In assembly, we're going to load a 0 into our accumulator. We're going to store that into our X register. Then we're going to use a loop label. We're going to do something. Then we're going to increment that value. Then we're going to compare that value to 255, and FF is 255 in hexadecimal. So next statement is branch not equivalent. So while it's not equivalent to 255, we're going to go back to loop and keep running that until it hits 255. Then when it does equal 255, then it's going to fall on through. It's going to continue on. So in a game programming language framework like XNA, we may have a couple of methods like draw and update for drawing something to the screen and updating the game engine. Well, in assembly, in the 6502 assembly, we're going to have a label NMI, that non-maskable interrupt, and that gets called on every frame. So when that gets called, we're going to modify our sprites, modify the background, and update the game engine code. Then we're going to use this RTI command, and that means return from interrupt. So that stops execution once it hits that RTI. So all sprites in all NES games, they can be created with a program such as YYCHR. There are other programs out there, but I like this one. It lets you easily draw to your pattern table. Each sprite is 8 by 8 pixels, and a sprite can only have 4 unique colors. It can actually have 3 colors and a transparency layer, so you're really limited on the number of colors you can use. Objects such as Mario are easily composed of multiple sprite tiles. So you can see down there in the picture there, Super Mario, he's actually composed of 8 different tiles. So you basically got to keep track of each of those tiles and put them on the screen appropriately so they make it look like one contiguous sprite. And all your sprites must fit on the sprite sheet. So I talked about palettes a little bit earlier. You have 60 or less than 60 total colors you can use on the NES. You write to the palette table by using the PPU IO port 2006 and 2007, and you write to these two locations, 3F10 and 3F00, to write the different palette data to that location in memory. So basically, you have 60 or less than 60 colors, but you have an even less number of actual colors that you can put on your palette. So the background from your game, so one screen is composed of 32 tiles across and 30 tiles down, and each tile is 8 by 8 pixels, which gives you a total resolution of 256 pixels across by 240 pixels down. And you can only have 4 unique colors for every 4 tiles, so that also limits what you can do in your game. And also, once you set the background, it's basically static, but you can scroll it left and right, and also up and down. And whenever you write text to the screen, there's no like printf or no drawstring statement. So basically what you have to do is you got to modify those tiles in the background using a text tile or a number tile, and that's how you actually display text to the screen. Controller input, actually this is fairly simple. Every time you want to read from the controller, basically you do a load from either memory address 4016 or 4017, either for player 1 or player 2. So every time you call a load from one of those address ports, then it will give you the status of one of the buttons on the controller. So the first time you do a load, it'll give you the status of A. If A is pressed, it will give you a non-zero value, not necessarily 1, but it will give you a non-zero value. If it is not pressed, it will return 0. So the next time you call it, then it's going to give you the status of B. Call it again, it'll give you select, start. Then it'll start giving you the statuses of the presses on the control pad, up, down, left, and right. And so to play sounds in your game, like music and sound effects, you have 5 different channels on the NES. You have 2 square channels, which gives you sort of a hollow sound. You have a triangle channel, which is a little bit more of a smooth sound. You have a noise channel, which is more of a scratchy type sound that you can use for like explosions and things like that. And then you have this DMC channel, and that's used for pre-recorded sounds such as voices. If you've ever played a game like Double Dribble or Blades of Steel, you can hear human voices in that game, and that's what it's using, is that DMC channel, and that uses quite a little bit more memory to play those types of sounds. And you write to this 4015 port to enable the sounds, and you use ports 4000 to 4003 to modify the sound properties, and that's what you use to make the different notes and determine the length of the notes and things like that. So I'm going to play a short video of what the sound waves in a game like Legend of Zelda sounds like. So you can see the two square waves at the top, and then you have the triangle wave in the lower left-hand corner. Then you have that the noise channel in the lower right-hand corner. So once you have your game written, you want to generate a ROM image, and these typically have a .NES file extension, and you have to use an NES assembler to generate this ROM. And I've always used this NES ASM3. That's guaranteed to work correctly and create a ROM image for you that is compatible with most NES emulators. There are other 6502 assemblers out there, but your mileage may vary with getting those to work. You might have to do some special things to get them to actually get your game to work on NES. But yeah, I stick with this NES ASM3. You also need an emulator to play your game. There are tons of emulators out there on the internet. Some of the older ones are like Nesticle and Rock NES and JNES. The one that I've found that a lot of people like to use for actually writing games is this FCE-UXD, and that gives you a lot more debugging options when writing your game. And also there's tools out there for actually playing the game that you've created on an actual NES system, and there's this Power Pack thing. I think it costs like $130 or so. You can find it online, and basically you copy your ROM image onto a flash drive, and then you can plug that flash drive into this Power Pack, and you put your Power Pack in the NES, and it should play your game. I don't have one myself, but it sounds like it works pretty well. So my game that I created for that competition is called Space Dude. It's a simple space shooter. I got a title screen, and I got a game screen, and you got your little ship, and it just shoots one bullet. You got 2 enemies that fly towards you. If you shoot the enemy, then your score increments by 1, and the enemy will disappear for a short period of time, then it'll eventually respawn so you can shoot the enemies again. So going to show the game here. Yeah, so here we go. Pull this over. So whenever my ship hits an enemy, I lose a life. And whenever I shoot the enemy, then he'll disappear. Actually, I just move him up to the upper right-hand corner of the screen, but I get 1 point every time that I shoot one of these guys. And once you get up to 10, then you start adding your values to the next digit. So it's a pretty simple game, but it shows like all the core features of an NES game. So if you want to actually start writing your own game, want more information than this brief lightning talk that I've given, I highly recommend checking out the Nerdy Nights tutorial at Nintendo Age. There's a link there, or you can just go into your favorite search engine, type Nerdy Nights, and that should be the first result you get. But yeah, it starts from the very beginning with just basically how to get a blank screen to display, to how to just display a sprite. Then it goes into how to move the sprite around and how to add background, and then it goes into a whole series of tutorials on music and how to get music to play in your game. This NES dev site is also a great reference. Tons of FAQs and tutorials and walkthroughs and things like that for creating an NES game. They also have an active NES developer forum, so you can go on there if you want to and ask people questions, or if you have a question, you can usually search the forums and your answer may already be out there. There's like a wealth of information on that site. And also, when I created my game, I created a post going through pretty much every step that I took in order to create that simple space shooter game. And also, if you want to know more about me, you can contact me, GodTechGrad, on Twitter. I've got a website, levidsmith.com. You can like me on Facebook, Levi D. Smith Software. And I currently have 2 games that are on the Xbox 3 Live Indie Game Marketplace. My first game is called Resistors, a simple puzzle game where you use resistors to connect electrical flow. And my second game is called TTY GFX Adventure, which is a classic RPG in the style of an old BBS game. So if you're into those types of games, check them out. You can also check out my Let 'em Dare page, where I have quite a few games. I try to do 1 game a month and post all those games out there. So that's it for my presentation, so I appreciate everyone watching. I hope you learned something, and yeah, let me know if you decide to create your own game. I'd like to check it out myself, so thank you.